Part 3 of our class today is a warm-up for our next class. In our next class we're going to be talking about section 10.5, and the topic there is solving trig equations. Now for the last couple of class periods we've been talking about trig identities. Trig identities are equations, but they're equations that are true no matter what theta or whatever angle you plug in. The equation will hold true. The left side will be equal to the right side. Now we are shifting gears into section 10.5, where we're going to talk about trig equations. And when we talk about a trig equation, that is not necessarily the same as an identity. Because when we're talking about a trig equation, we are asking for what values of theta or for what values of x or whatever our variable is, what values of that variable make the equation true. So our equation is not true for all theta, but only for a certain number of, or certain values of theta. So today, in this part of our lecture, we are going to look at two examples that are kind of a warm-up and to kind of get the juices flowing in terms of thinking about solving these trig equations. And our first example, we are asked to find all values for theta, where theta is between 0 and 360 degrees, that are solutions to sine of theta equals 1/2. Okay, so when I see up there that theta is between 0 and 360 degrees, what that part tells me is that tells me two things. That tells me that our final answers should be in degrees rather than radians, because our theta is between 0, and that should really be 0 degrees, and 360 degrees. The other thing that this theta between 0 and 360 degrees tells me is that we only need to go around the circle or around the xy plane exactly once. If we go higher than that, then we'll be looking at angles larger than 360 degrees, and if we swing clockwise, we'll look at negative angles, and we do not need to worry about that. We just want to look one time around the circle. So that's what that piece of information tells us. Okay, so now let's take a closer look at sine of theta equals 1/2. All right. Now the first thing I notice is that we're trying to find an angle of theta somewhere between 0 and 360 degrees, and the output that I have is positive. And so thinking about that, what that tells me is that when I'm looking for my angles, I want to think about looking for angles in quadrants where sine is positive. And I know that sine is positive in quadrant 1, and sine is y over r, so the other quadrant where y is positive is in quadrant 2. So sine is positive in quadrants 1 and quadrant 2. Now, that also means that since sine is negative in quadrant 3 and 4, I can ignore those quadrants completely. Okay, so that's the first thing that I want to think about. And so now I know that I'm going to have an angle that will be in quadrant 1 and in quadrant 2. That will be angles that will be answers to sine of theta equals 1/2. All right, so I've drawn an angle in quadrant 1 and an angle in quadrant 2. I don't know exactly what the values are, so I've just kind of drawn them in there. All right, now the next thing that I want to think about is that sine of theta is opposite over hypotenuse, or y over r. So in my drawing, in the xy plane, I'm going to turn these angles into triangles. And so by knowing that sine of theta is opposite over hypotenuse, or y over r, when in the problem it says sine of theta equals 1/2, that means that my y value on my triangle can be 1, and my hypotenuse, or r, will be 2. And the same is true on the triangle in quadrant 2. The y value is 1, the r value is 2. And so now I want to ask myself, okay, do I know any triangles where I have one side that has a length of 1 and a hypotenuse of 2? And the answer is yes, I do. I know a triangle that has a hypotenuse of 2 and a side of 1, and the third side on that right triangle is square root of 3, and that angle, opposite of 1, is a 30-degree angle. So in my picture, in quadrant 1, I have a triangle whose reference angle is 30 degrees, and in quadrant 2, I have a triangle whose reference angle is 30 degrees. Okay, so we are almost done now. The last thing that I want to think about is, now that I know what the reference angles are, the actual angles that we're talking about are angles that start on the x-axis and end either in quadrant 1 or in quadrant 3. So the first angle in quadrant 1, well, that's the same as the reference angle, that's 30 degrees. So one of our values for theta will be 30 degrees, and the other value for theta, we want to swing, I'll pick a different color for this one. We start on the x-axis, and we end in quadrant 2. The reference angle there is 30 degrees, so the angle that I'm interested in is 30 degrees short of 180, so that angle is 150 degrees. So our second possibility for theta is theta equals 150 degrees. Okay, so what we've just done is we have solved the equation sine of theta equals 1/2, and we found that theta equals 30 degrees and theta can be equal to 150 degrees. If you want to, you can check that in your calculator. If you have your calculator in if you have your calculator in degree mode and you type in sine of 30 degrees, the output should be 1/2. And if you have theta equals 150 and you type in sine of 150 degrees, your output should also be 1/2. Okay, let's do another example of one of these as a second warm-up problem. In this example, we are asked to find all values for theta, where theta is between 0 and 2 pi, all the values of theta that satisfy the equation cosine of theta is equal to negative square root of 2 over 2. Alright, now the very first thing that I see here is that we're looking at theta between 0 and 2 pi. So because we're given 0 and 2 pi and there's no degree marks on those, that means that these are angle values that are in radians. So our values for theta should be in terms of radians. And because theta is we're looking for theta between 0 and 2 pi, we are only looking one time around the circle. Okay, so now we are going to look at the equation that we're given, which is cosine of theta is equal to negative root 2 over 2. Alright, now our goal is to figure out angles of theta, where cosine of theta is equal to negative root 2 over 2. So the first thing that I see here is that this value is a negative value, and cosine, which is x over r, is negative in, let's see, negative in the quadrants where x is negative, so that's going to be on the left side. So quadrant 2 and quadrant 3. So I know that I'm looking for angles in quadrant 2 and quadrant 3, and I'm ignoring quadrants 1 and 4. Alright, so I don't know what the angles are, but I'm going to go ahead and draw them. Here they are. Here's one angle. Here's one in quadrant 2. Here's an angle in quadrant 4, and I'm going to create the two triangles there. So I've got one triangle in quadrant 2 and a second triangle in quadrant 3. All right, the next thing I want to think about is that we are told that cosine of theta is negative root 2 over 2, but I recognize this number, at least the root 2 over 2 part, and I know that root 2 over 2 comes from the rationalization of 1 over square root of 2. And so root 2 over 2 is the same as 1 over root 2. And that's helpful for me because I can then think of cosine of theta as negative 1 over square root of 2. And when I'm thinking about the cosine function is x over r, or adjacent over hypotenuse. So if I label the x side on my triangles, my x is negative 1. That makes sense because we're on the negative x side. And our r value is square root of 2. And that's true on both triangles. Okay, so now I ask myself, can I think of a triangle that has as its hypotenuse square root of 2, and one of its legs has a length of 1. I don't worry about the negative if I'm not drawing this on the xy plane. And the answer is yes. I do know a triangle like this. This is one of my special triangles. And I have a 45-degree angle, so this is a 45-45 right triangle. One of my legs is 1, the other leg is 1, and my hypotenuse is square root of 2. Now this is pretty cool because that means that I know what these two reference angles are. These two reference angles are 45 degrees each. Okay, now that I've used all the information I have to come up with these triangles, and I know their reference angles, now I want to think about what are the angles in standard position that give us these 45-degree reference triangles. All right, now, in this particular problem, we are asked to look at angles between 0 and 2 pi. So we're talking about radian measure. So 45 degrees is the same as pi over 4 radians. And so I have a couple of different ways I can think about this. One way that I think is kind of nice is to think about breaking the xy plane up into blocks of pi over 4 or blocks of 45. So if I do that, here are some dashes. Each of these blocks are pi over 4. And so to get to our first angle, the angle in quadrant 2, I have 1, 2, 3 of these pi over 4s. So our first value for theta is going to be theta equals 3 pi over 4. And for our second angle, we have 1, 2, 3, 4, and 5 of these pi over 4s to get to an angle in the third quadrant with a reference angle of pi over 4. So our second angle is theta equals 5 pi over 4. And so our final answer is that if cosine of theta is equal to negative root 2 over 2, then the angles in the xy plane are theta equals 3 pi over 4 and theta equals 5 pi over 4. And again, you can check that in your calculator. Make sure your calculator's in radian mode and type in cosine of 3 pi over 4, and you should get as an output the decimal approximation of negative root 2 over 2. And the same thing should happen if you type in theta equals 5 pi over 4. Okay, thanks for listening.